All right, so we're going to carry on now with this section. This is actually chapter 5B. And right now we're going to look at a couple of interesting results involving integrals. We'll start with the average function or average value of a function. And so what this is telling us is that over a given interval, let's draw a little sketch here. Let's say this is A and this is B. We already know that the area under this curve between these 2 points can be calculated as the definite integral of our function between A and B. But now what we're going to be seeing here is that if we now take that result and divide it by 1 over B minus A, what we'll end up with is the average value of the function over that interval. Okay, so there's the total area is right here, but the average over the interval, the closed interval from A to B, is going to be the definite integral from A to B multiplied by 1 over B minus A, where of course that means that's the width of the interval. Okay, so now this comes from a very important result in calculus called the mean value theorem for integrals. And what it basically says is that if we have a continuous function over a given interval, it must assume its average value at some point over that interval. In other words, as long as it's closed and continuous, it's not possible for the function to avoid hitting its average value at some point. So that's where this is actually coming from. Of course, again, remember, this assumes that the function is continuous. If it's not continuous, of course, it could skip around and completely avoid that average point. But since it's assumed to be continuous over that interval, then it must reach that point. And in fact, there must be some point C in that interval where we're reaching that average value. Okay, so in other words, if we draw that graph again, all right, once again, here's A, here's B. Clearly, the function is continuous over this interval at least. We don't know what's going on anywhere else, but we do know that between A and B, it's continuous. What they're saying here is that there's some point C in here at which it reaches its average value, and that average is f of C. Okay, so that's what we're getting from the mean value theorem. And the consequence of that is that because f of C equals the integral, the definite integral from A to B times 1 over B minus A, we could rearrange that algebraically, and we end up with this result. And so now we can use this to calculate average values. For example, what if we have the function f of x equals 8 minus 2x over the interval 0, 4? Let's find the value C such that f of C equals that average value. All right, well, first things first, as we saw earlier, f of C, whatever that C is, we don't know what it is yet. Now, we've all already been told that the interval is 0 to 4. So, of course, that means that A is 0 and B is 4. And furthermore, we were told that the function itself, f of x, is 8 minus 2x. Okay, so we can plug in all these numbers, and you can see here we've started to do that. 1 over 4 minus 0, and we have the interval from 0 to 4. The function is 8 minus 2x dx. And then, let's see, we can, now actually in this case, it turns out we can do this with geometry as well as calculus. But why don't we carry on with the calculus part first? Let's say that we continue with this example. We have f of c, and so we have 1/4, 0 to 4, 8 minus 2x dx. Okay, now, of course, I can factor out the 1/4. And I can also break this integral up into two pieces. And of course, I think it's a good habit to move the constants on the outside of the integral sign. It's just easier to figure out what you're supposed to do. It's not that important when they're simple integrals, but sometimes it can make a big difference in figuring out which approach is the best. So we have 1/4 times 8 inside the parentheses. I move the 8 outside, so we have 8 integral dx minus 2 times integral of x dx. So what do I have? 1/4. This is 8. Now the dx, when it's integrated, becomes x. And so we evaluate that from 0 to 4. And over here, we have minus 2 times x squared over 2 from the power rule. Okay. Oops, I didn't draw this correctly. Sorry, hold on 1 second. This is supposed to be a parenthesis. Okay, because we've evaluated the two integrals. There we go. Okay. All right, let's see what this turns out to be. Actually, there's one more simplification that we can make. Maybe we'll do that. Why not? I like to keep things as simple as possible. Yeah. See, sometimes this draw, it doesn't always copy that well, so I'll just manually copy it. So anyway, what I was getting at is that here, these two, the 2 and the 2 down here cancel each other out. So I've actually got minus x squared evaluated from 0 to 4. So I can rewrite that as 1/4, 8. Inside the parentheses, I have 4 minus 0. And over here, I have 16 minus 0 because this would be 4 squared minus 0 squared. Then we have 1/4, 8 times 4 minus 16 was 1/4 of 32 minus 16, 1/4 of 16, and that would be 4. So in other words, the average value of this function over the interval from 0 to 4 is 4. Now, it's easier to see this visually when you see the graph because the function we started out with is simply a straight line. Okay, so that's what it looks like. And of course, the interval we chose for was 0 to 4. And so you can see here that the average is 4. But how do we figure that out? Well, at the point c equals 2, if you look at the area of this rectangle, the entire rectangle has an area of the base times the height. The base is 4. The height is 4. Okay. So the average would be 16 divided by 4 minus 0, because that's the width of this interval. And that's equal to 16 over 4, which is just 4. Now, by the way, how do you know that c is 2? Even having this result, f of c is 8 minus 2x. Okay, so what that tells me is that whatever the value of c is, 4 equals 8 minus 2x. There it is. Okay. So what this means then is that not only is the average area between 0 and 4 equal to 4, but the average is reached when x equals 2. Okay. So that's how, and now, and of course, and this is the simplest case to consider. Normally, it would be very difficult to see this even with a graph, but with a simple function like this, it's easier to see exactly what's happening here. All right, so now we're going to introduce a very important result in calculus called the fundamental theorem of calculus, which essentially justifies what we've been doing with our definite integrals. Okay, it's basically the reason why we're able to calculate areas with definite integrals. Now, by the way, anytime you run into a theorem in any discipline, that turns out to be a very important result, but especially if the word fundamental is there. You don't see a lot of fundamental theorems in any discipline, including math. So when you run into one, that means it's important. So this is the fundamental theorem of calculus. And so it's actually broken up into two distinct parts. It's the second one that we'll really be using most of the time. But the first statement of it, the first half of it says, if f of x is continuous over the interval ab, okay, of course, we already have seen enough times that the area here is equal to the integral, but, and also don't forget the notation we're using is that capital F of x is the antiderivative or integral of f of x. So what this is telling us is that this is defined as the area from a to x, whatever x is, and that then we integrate f of t dt. By the way, I just want to notice you to notice here there's a t here. This is x and this is t. So what's happening here is that we can't have x twice. I mean, we can't use it for two different purposes. Here, x is being used as the upper limit of this integral, but it's also the variable. So what we have to do is we change this to some other variable, which is sometimes called a dummy variable. It could be literally any other letter that we choose, even a Greek letter if you really want to. The purpose of doing it that way is so that it doesn't get confused with the upper limit of the integral. Okay, so we're integrating the function from a to x. And so what it's telling us is that if you take the derivative of the antiderivative, you'll end up with the original function. Okay, over that same interval. All right, so here's a numerical example of this. So here we have g of x is the integral from a to x of 1 over t cubed plus 1 dt. And so what we're being told here is that g prime of x is just this function where the t's are being, I mean, this is what it actually implies, that it's that just that function, except that we're replacing the t's with the original x. So what they're really telling us in so many words here is that the advantage of this is that we don't have to deal with Riemann sums. Okay, in other words, you know, when you first are introduced to integrals, you're being shown how they are defined in terms of Riemann sums, which is fine, but it can be a very time-consuming process because then we have to take a bunch of limits. So this makes it possible to have formulas instead of dealing with limits of sums when we're solving for antiderivatives or integrals. Now, it's the second one that we're really the most interested in. the second part of the fundamental theorem tells us that the integral from A to B. So let me see if I can draw this with a proper graph. Is equal to let's see, how am I going to do this? Oh, all right, I have an idea. F of B is the integral. Now, the antiderivative evaluated at B. F of A is the integral evaluated at A. So in other words, what they're saying is that this range here is equal to the difference between F of B, which is basically, think of this as the entire area under this curve all the way down to negative infinity. And then F of A would be the entire area under this curve all the way down to negative infinity. Okay. Oh, Jesus. Let me just fix this. All right, let me make that a little neater. So the difference between them is what's left over. Okay, so in other words, if capital F of B is the area under this curve all the way down to negative infinity, and the area capital F of A is the area of under this curve from A all the way down to infinity, negative infinity, then the difference between the two of them is the shaded region. Okay, so that's what this is telling us. That you could calculate this area as the difference between two integrals. So like, here we go. Let's look at this case. We have the integral of x squared over the interval from -2 to +2. Okay. So what we're going to do is, first of all, obviously we're going to use the power rule. Evaluating this between negative and +2. All right. So what do we have? 8/3 minus 8/3. So actually, let me write some more of this in the next slide here. So we've done this before, but what they're doing now is telling us that let's write it like this. Think of this as capital F of 2, and this is capital F of -2, because that is the integral evaluated over that interval. Okay, so so therefore we have 8/3 minus -8/3, which is 8/3 plus 8/3, which is 16/3. Now, nothing's really changed. I mean, this is what we've been doing all along. It's just that now we're thinking of it in terms of two different antiderivatives or two different integrals. But it's the fundamental theorem of calculus that